Good.
Hi, so this is the final demo for Group 3. We are the laser beam characterizer. This is the bottom layer of our system. This is the base plate that we'll be using, and this is just an extra plate to help us align our laser to the system. Here we have our laser coming out of a fiber and into a collimator. It's then aligned with these two mirrors to these two irises. These are our reference irises that the user will align their laser to in order to make sure the beam goes through the system properly. Immediately after the irises is this polar emitter setup. We have our quarter wave plate here, and on the back here is the linear polarizer. Then we're going to go from here, this mirror, and this mirror, we'll redirect it over here. This is our 800 millimeter focal length lens. This is our beam sampler that's going to reflect 5% over here to this mirror, where the beam will be translated up, and then our top layer microsync interferometer will go here, and we'll measure wavelength through there. So from here, the 5% goes here, but the rest of it goes through here. And these two mirrors are aligned on this translation stage in order to scan across the path of the beam. Here, where we have our fan blades run by our DC motors, where we perform our knife edge test. So here we have our microsync interferometer on top of our system. So again, we have our beam sampler here, and it's going to reflect the beam up to this mirror, where it's going to go into the interferometer. We have our beam splitter here. It's got a 50-50 split, so it's going to go to both of these mirrors. And this mirror we have on a stage that's going to move back and forth so that we can change the optical path length difference between the two arms. And then we have our photodiode here where we can measure the signal. And so hopefully, if the speed of the mirror is fast enough and the responsivity is high enough for this, then we should be able to see a good sinusoidal signal by which we can extract the wavelength of light.
So here we have our main PCB board with the STM microcontroller chip, our voltage regulators at 3.3 and a 5 volt. We have 3 stepper motors. We have one going to our translation stage. We have one going to another translation stage. And then we have another one going to our quarter wave plate. And we have a variable TIA that controls our gain stages. We have a DC motor connected to our beam profiler. And then we have the DC motor encoder controller.
So here on our translation stage for our beam quality and divergence testing, we have our 2 mirrors going into our profiler. And here at the end here, we have a little push button here. So that way when the stage moves all the way, it'll hit the button, and then this will home the motor so we know exactly where it is, and then can reference all of our points from this.
For our variable transimpedance amplifier, is used to amplify the power read by the 4 lamps power meter photodiode. There are 4 gain states to this variable TIA with resistors of 1.3K, 13K, 130K, and 1.3 megohms. This gives a gain of 10x every single stage. So originally, the gain states were wired in series, and the switches would short which resistor would which resistors were not needed for the gain state. But there was a weird nonlinearity that we saw where in gain stages 2 and 3, there was a huge spike in gain with a small amount of power, and it was really not nonlinear. So this caused us to have to redesign a little bit. And so we rewired these to be in parallel, and it gave us much more consistent results. So at our responsivity at our tested wavelength was about 21.3 milliamps per watt. And so we performed a power versus voltage sweep to determine the transfer function of the TIA. So here are the results that we have. So for stage 1, since the gain is super low, we were limited by the power of our laser, so we only got a few points there. But you can still see a pretty good linear response on all of these stages, and the fit is very well. We calculated the effective feedback resistance of each state, given the known responsivity at our wavelength. With the first stage, it's a little bit just because of the on resistance of the voltage controlled switch, and all the other ones are consistent. The polar emitter, we have a custom-made quarter wave plate and linear polarizer mount, as we showed in the video earlier. Uh, it's going to need a little bit more calibration, but the results that we obtained from this are fairly consistent. For horizontal polarization, we have pretty close to the expected results with a measured angle of only -3 degrees. And for circular polarization, we saw that the ellipticity was about 38.8 degrees, which is pretty consistent, which for an ellipticity angle of 45 degrees for a perfect circular polarization. There's a little bit more stuff we can do for this to improve it. For instance, implementing a homing mechanism to identify more precisely where the position of the quarter wave plate is relative to the linear polarizer. So here are the results for the horizontal polarization. See the pretty power curve and the polarization ellipse plotted on the right. And here are the results for the circular polarization. You can see that it is also a very curve and gives a very circular response.
For the beam profiling results, we have been able to get pretty consistent calculations of the beam width during our test runs. We have the STM running the beam profiler program until it has 10 valid scans, and it discards any invalid scans it finds, as seen on the left. And then after it collects all the scan data from both axes, the Python script will report a summary of the scans, and then it will average the scans into a single beam width calculation.
So for the interferometer setup, I used a Heaney laser to get a basic alignment, and I obtained a very good interference pattern, as you can see on the bottom right there. The rings are obtained by putting a lens in front of the interferometer, and this makes it nice and clear where I can put our photodiode right in the center there, and then as the mirror moves, the rings expand, they grow, they move outward. We've been having a little bit issues with our stepper motors, so we've been unable to get precise measurements with our MCU, but we are still working on that. So we do have some previous data on this though. This is using a Heaney laser and a different photodiode. So we were able to just look at this on an oscilloscope, and we can see that we obtain pretty good results at different sampling rates. we were able to get fairly close, fairly good resolution. And we're hoping to sample at sample per second, which should give us fairly good resolution. And with a little bit of data analysis, I think we can get close to that 1 nanometer resolution that we're looking for.